Today we are going to begin our discussion on redox reactions and start to be able to define oxidation numbers, and then a subsequent lecture will look at actually classifying different types of redox reactions. So whenever we talk about oxidation or oxidation reduction reactions, another way we'll refer to this is redox reactions. Okay, so a redox reaction is talking about the transfer of electrons between species. So let's go ahead and look at this example right here. So we have sodium plus chlorine yields sodium chloride. So notice that sodium has no charge on it, and neither does chlorine. But then whenever we form sodium chloride, we know that sodium chloride is made up of a cation and an anion. So sodium has a +1 charge and chloride has a -1 charge, okay? So if we were to look at the half reactions, what we'll see is there's a transfer of electrons. We said that sodium is the cation, so it's losing electrons, and chloride is the anion, so it's gaining electrons. And that's what these half reactions down here represent. So we have sodium going on to form the sodium cation plus 2 electrons, because we need 2 sodium ions here for a balanced chemical reaction. And then we have chlorine, which exists as a homonuclear diatomic, one of those 7 at 7, and it gains 2 electrons to form 2 chloride ions. And whenever these combine, we have sodium chloride. So let's go ahead and define a little bit of the terminology for redox reactions. So one of the ways that we try to remember what oxidation and reduction is the saying oil rig. So oil rig stands for oxidation is loss of electrons, whereas reduction is gain of electrons. So if we go back and look at that previous example, we can see that sodium is losing electrons. So since sodium is losing electrons, it is being oxidized. Okay, and then chlorine right here is gaining electrons, so we could say that chlorine is being reduced. So remember that oxidation is loss of electrons, which will lead to an increase in oxidation number, which means you're getting more positive. Okay, reduction is gain of electrons, so you're going to have a decrease in oxidation number, which means you're becoming more negative. So another way that you'll see this written occasionally is in terms of the reducing agent or oxidizing agent, and this is completely opposite from oxidation and reduction. So the reducing agent is actually the species that is being oxidized, and the oxidizing agent is the species that is actually being reduced. So if we go back and look at this previous example, so sodium is being oxidized, so that means that sodium is actually the reducing agent. Okay, chlorine is being reduced, which means it's the oxidizing agent. So how do we define oxidation numbers? Well, I've made a list of kind of the hierarchy of assigning oxidation numbers. And so whenever we assign oxidation numbers, what we're assuming is what we're asking is, what is the charge on the atoms if the compound was actually ionic? Many times it's a molecular compound, so we're having a sharing of electrons. The electrons aren't actually being physically transferred like they are in an ionic compound. So, but if a compound was ionic, what would the charge be? So the first thing is the oxidation number of an elemental substance is 0. Well, what does that actually mean? Well, that means if you have, for instance, solid silver, or maybe you have neon gas, or hydrogen gas, something like that. Those are all in elemental form. And if you are in elemental form, then your oxidation number is 0. So the next one we're going to talk about is the monatomic ion. Okay, so monatomic, mono means 1. So for instance, if we had magnesium 2+, okay, magnesium 2+ would have a +2 oxidation number. Notice that whenever we're talking about the charge, it's 2+, 2-, 3+, 3-, something like that. But whenever we're talking about the oxidation number, we list the sign first and then the value. Okay, so the next common oxidation number that you would assign would be for the alkali earth metals. So this is column number 1 on your periodic table. So this is like sodium and potassium. These would have a +1 charge. And then also the alkaline earth metals. So for instance, magnesium and things in group 2, they would have a +2 charge. Okay, so then once we get out from there, let's go ahead and talk about the oxidation for common nonmetals. So this is kind of the hierarchy that you would use for assigning these. You would assign hydrogen first, then oxygen, and then halogens. Hydrogen is +1 if it's behaving as the cation, but if it's behaving as an anion, it's -1. Okay, so then hydrogen ranks higher than oxygen. So oxygen has a -2 charge. Okay, and then the halogens have a -1 if they're behaving as the anion, but if they're behaving as the cation, then you need to calculate, okay? And that's for the halogens. Whenever we talk about rank, what I'm saying is which order would you assign the oxidation numbers in? And we'll go ahead and do a few practice problems. But more or less what we're trying to do is we're trying to get the sum of all of the oxidation numbers to equal the charge on the compound. Let's go ahead and do a few together. And again, I wrote this up here. The overall charge is equal to X. So X would be however many there are of your first component times its charge, plus Y, which might be your second component times its charge, plus Z, which would be the Zth component times its charge. So for H2S, okay, the overall charge is 0. So 0 equals, well, we know that hydrogen has an oxidation number of +1. So we're trying to figure out what the oxidation number is on sulfur. So we would take, well, how many hydrogens do we have? We have 2 hydrogens, so we take 2 times its charge, which is +1, its oxidation number, plus how many sulfurs do we have? Well, we only have 1 sulfur, and we don't know the charge, so let's go ahead and call that X. So we need to solve for X. And once we solve for X, we'll see that X equals -2. So sulfur has an oxidation number of -2. Okay? So now let's go ahead and look at another one, H2O2. So again, we would rank hydrogen higher in our hierarchy than oxygen. So hydrogen has a +1 oxidation number. And we know that oxygen is typically -2, but if we put -2 here as the oxidation number, well, if we set up our equation, we'd have 2 times hydrogen, which is +1, plus 2 oxygens times its oxidation number of -2. This does not equal 0. So what that means is oxygen must have a different oxidation number. So let's go ahead and go through and try to solve for that. So again, hydrogen we know has a +1 oxidation number. There's no charge, so we're going to set this equal to 0. There's 2 oxygens, and we don't know the oxidation number on it, so we'll call that X. So we can end up writing that 0 is equal to 2 plus 2X. So X equals -1. So oxygen has an oxidation number of -1 in the species hydrogen peroxide. All right, let's take a look at another example. So here's our first example where the overall charge is not 0. So the overall charge is -2. So negative 2 equals, well, do we know the oxidation number on sulfur? Well, it was negative 2 on a previous example, but we don't know for sure. So that's what we're going to try to solve for, because it looks like here sulfur is going to be behaving as the cation or whatever is going to be giving up the electrons. So we only have one sulfur, so we'll call that X plus, how many oxygens do we have? We have 4 oxygens, each with a negative 2 charge. So as we write this out, we have negative 2 is equal to X minus 8. So that means X equals positive 6. So sulfur has a positive 6 oxidation number, oxygen has a minus 2 oxidation number, and overall sulfate has a charge of negative 2. So you can go about finding the oxidation number like that. So then for potassium nitrate, okay, well, potassium has the highest ranking for us. Potassium we know is an alkali earth metal, so it has a +1 oxidation number. Oxygen has a -2 oxidation number. So let's go ahead and set up our equation. There's no charge overall, so it's 0. It's equal to 1 potassium times +1. We don't know the oxidation number on nitrogen, and there's one of them, so we'll call that X plus 3 times -2, the oxidation number for oxygen. Okay, so as we write this out, we'll end up with 0 is equal to X plus 1 minus 6. So X is going to equal +5. So nitrogen has a +5 oxidation number. All right, so let's go ahead and look at some examples in an actual oxidation reduction reaction. So we need to determine whether each reaction is a redox reaction. For a redox reaction, what we'll have is a change in oxidation numbers. And then we need to identify what's the oxidant and what's the reductant. So let's go ahead and go through. So for the first example, gallium, it's then all by itself, no charge, so it has an oxidation number of 0. Same thing for bromine, it's all by itself, so it has a charge of 0. So let's go ahead and figure out what the charge is over here for gallium-3 bromide. So over here, bromide is a halogen, so we know it has an oxidation number of -1. So if we set up our equation off to the side, there's no charge overall, so 0 is equal to X, which is the oxidation number of gallium, plus 3 times -1. So we know that the oxidation number of gallium is +3. So the oxidation number's changed, so that means that this is a redox reaction. Okay, gallium went from 0 to +3, so that means it lost electrons, so it's being oxidized, so it's the reducing agent. And bromine gained electrons, so it's being reduced and is the oxidizing agent. Let's go ahead and look at the next two. So for zinc carbonate, okay, we already know that oxygen is -2. Okay, zinc's going to be +2 because carbonate, CO3, has a 2- charge, so that means zinc has to have a +2 charge. Okay, so as we look at this and we're trying to figure out the overall charge on carbon, we have 0 is equal to +2 plus X, and then we have 3 oxygens, each at -2, so that'll be -6. So what we'll end up having here is carbon has a +4 oxidation number. Over here for zinc oxide, oxygen has a -2 charge, or a -2 oxidation number, which means zinc would have a +2 oxidation number. And then for carbon dioxide, oxygen has a -2 oxidation number, which means carbon is going to end up having a +4 oxidation number. So as we look at this, notice that none of the oxidation numbers changed. So that means that this is not a redox reaction. All right, why don't you guys go ahead and try to assign the oxidation numbers on the next one by yourself, and then we'll go over that in class. In the next lecture, we'll start to look at different types of redox reactions and assign the types.